Today I want to extend my lectures on what we're doing with induction. Remember, induction is a type of reasoning. It pairs well with deduction. Deduction is when we argue from the evidence we have using logical operators. Induction is when we generalize from the patterns we have using logical operators. But there comes a time when we want to do something like a computation. Computation often needs exact evidence, real data to move around. Otherwise, what's the computer going to use? The word induction in that case starts to be very specialized. What we do is we think about the scenarios in which our data would arrive. If that data would arrive to us in inductive ways, meaning we don't really know what it'll do, but it follows some patterns, we try to write down what those patterns would do, and we compute with respect to those patterns. I have behind me one of the most common patterns used today on the internet. It's known as JSON, JavaScript Object Notation. It's a primarily text interface for data, where we label the information by useful names. There are a few keywords that keep track of what type of data we have, but as we define new data types, we can also include new defaults. When we collect them together, the whole thing is known as a JSON blob. If we look at the ingredients, we can see that there's some general structure. We have open braces and closed braces to gather together individual parts. Those can occur inside as well. We can have subparts of our bigger parts, and therefore blobs can get larger and larger over time. We also label everything with a beginning name, usually in quotes, and then a semicolon, followed by whatever data we want. Now, if I look at the way this information is structured, I can see that I've named a string with the word induction. I have a number, which is specifically 541. Boolean is set to true, and then I have one called object, which looks like a copy of our JSON in miniature. It's a nested example. You might think of drawing this with a graph such as a tree, with the top node being the entire blob and its leaves being all the individual pieces we see here. That might look like this. If I look here, I have one branch for our string, the induction word, one branch for our number 541, our Boolean we should put true, and then for our object, we've simply branched again into now two new types of branches, one called base, one called next. The base here had 17.2, and the next had Taekwondo. The idea of JSON is to be very flexible about adding new types as necessary, as applications can't all be designed around just the primitives we might think of. So it might make sense to have base and next, and another place to simply have words like string and object, which are preloaded with some predetermined understanding of the data types. Now, if we want to get this information into that shape inside the computer, we need to create our own data types. Our data types need to have this kind of branching behavior. But we want to maintain the behavior that when we're done creating one of these blobs, we can fit it inside of the next blob. That is, at the end of the day, everything we build should be one common data type, a JSON blob data type. To do that, we use inductive constructions. Now, there's several techniques that have happened over the course of software design for implementing inductive data types. Historically, there was a lot of hierarchies. You would make an abstract class and subtype it with various subclasses. That led to typecasting rules and the idea of interfaces, traits, and mix-ins, and many other ways to solve the problem. Today, most programming languages, however, have some built-in data structures for building inductive types. Let's take a look at some of the possible syntaxes. Let's begin with a language called OCaml. This is part of a general family known as ML. In this model, data is introduced as a type, and then we give it a name. In this case, I'm choosing to call it bit. In order to give the introductions, the data we want to introduce of type bit, this language simply needs to have them listed next to the vertical stroke. In this case, I'm using up and down instead of 0 and 1. Once I have created the data type, I need a method to use it. What I'm going to do is make a program that prints out the digit 5 when I use up, and the word 5 when I use down. In our function, we have let as 5. We see then that to execute the computation, we used an intermediate type called nat or string. Its role is simply to fuse together two different types of numbers. One is a natural number, and the other one is a string. Remember that left and right are choices we make to glue together disjoint unions. In this case, the left are the natural numbers and the rights are the strings. Taken together, there's our entire program in ML. Now let's try this in a language similar to Python and Java. This is known as Scala. Here, the keyword to use is trait, and we've also added a keyword sealed. The sealed word is that we don't want to add to our options. I then create the different cases. In this case, I want up arrow to extend B and down arrow to extend B as well. This is similar to how hierarchies were used in older programming languages. But the case distinction is letting us write simpler programs to use it. Once more, we want to bind together our results. On the left, we want integers. On the right, we want strings. This will depend on whether our arrow is up or down. Using the pattern matching, we want the case of the up arrow to give us the left number 5, and the down arrow to give us the right word 5. Now that we've seen some of the syntaxes that we could use, let's take this information and try to write one possible data type that could cover the cases we see here. I'm going to start out by creating a syntax for a data type called JSON. This could be preceded by the word data, but I'm going to use the word class for this example. Then I'm going to list all the cases. Once more, there's several syntax, a vertical stripe separating cases, or the word case, as is often used. I'm going to make the assumption that our data structures are living inside of a context where there's already several good program data types, such as a primitive for strings and integers, and many other types, arrays, and so forth. This allows me to use the optimal methods in those programming languages. So the issue now is that I'm going to read a string out of my file and try to convert it to a string inside of my programming language. Assuming that the programming language was built first, it's already used the word string. So my constructor has to use a new name. I'll use asString. I create my class JSON, and asString says to read in the actual string value and populate it inside of an internal data structure called string. That's the first case that I could read, but there's other cases. So the next case might be read a number. I'll also need to be able to read in booleans. And finally, I need to deal with the case of reading in an object. Now here we want to be careful, because what we're having is a JSON blob that already exists being passed in as part of the data to my new JSON blob. So I could add that this way. I can create a JSON blob given one that already exists. This will be the case where I've labeled it as an object. Finally, the collection of all of them is just a long list of various JSON blobs. I've added 2 new constructors to capture the situations that could occur. I need some place to start out, such as an empty JSON file. 2 empty braces, no information to pass along, but it's a starting point. If I've started with something else, that's okay too. The next is that I need to pair things off and whether they've been separated by these commas. So if I built a JSON on the front and a JSON on the back, I simply pack them together. This is enough information to glue together the information that we've seen. Now, there's other ways to do this that might be more efficient. We're simply trying to gather a data structure that captures all the information we need to read out of the file and put it into our computer in a way that can structure things recursively. Now, what we've talked about so far are just the constructors, the introduction rules. We want to be able to use this. This is where an abstraction that comes from the world of algebra can be a useful way to interpret the ways we use inductive types. Let's pause to imagine that JSON was reduced to a single letter, just the letter J, and let's look at the structure of the data and its movements. In order to gain some extra intuition as to what we could do to model this problem and its behavior, I've written down here an encoding of these cases. What I've done is I've written as J the letter to represent any kind of JSON data. And then I've written the ways that we could introduce it. Notice I've only been interested in whether there are new inputs from the JSON side or not. For example, in the case of a string, the only input is a string. I don't need a pre-existing JSON blob to add to it. The same is true for a number and for a Boolean. Each of these produce a JSON. When it comes to the blob, that's when we actually take in a JSON object. One single JSON blob produces one single JSON blob out. When it comes to concatenating, that's when we take in 2 values, and so I've written a 2-value input. Going back to the case of 0 inputs, that's often denoted by a pair of parentheses. That's because of the following convention on sets. When we write x to the n with sets, we mean to think about all the n tuples of values coming from x. So for example, x squared are ordered pairs. X to the 1 is just a single value from each, x cubed would be 3 triples, and x to the 0 is a pair of parentheses. Keep in mind, such a set still has one element, only one element, and so x to the 0 has size 1. Just like we think of any other number, 10 to the 0 is also equal to 1. So each one of these is actually a set with one thing in it, and therefore it has a unique output out, the constant we're thinking of. In this case, the constant of this function will be the value s. This one will be the value n, and so forth. If we wanted to include that in the syntax over here, we could include an extra pair of parentheses for where all the JSON stuff comes from. We can see that I've added empty parentheses to the ones that are constant, but I have the parentheses that have the number of JSONs to capture all the ones that depend on actual Js. We might even rename this function to match this cat name. The reason to want to name just the JSON blobs is because we want to think about the data as evolving over time. Some of these are pretty straightforward. If you give me a string, I can do string-like things to it. If you give me a number, I know what to do with number-like things. But once you give me a pair of JSON blobs, I'm going to need to get their meaning by asking the individual parts, what are you about? Do you have strings, booleans, and integers? What about you? Because these parts will be done inductively, it helps to separate the parts that will be repeated as extra copies of J and keep the process what we know as homogeneous. Homogeneous means that they're all the same values. You can see all of these depend only on J's and produce things in J. They might also represent some other values, but those are constant for the purposes of thinking about JSON blobs. A string remains a string remains a string, a number remains a number. Here's a more comprehensive list of some of the JSON operators that we could have. For example, I've added an as array, which lets us have a vector of different JSONs of different lengths. For example, if the length was 2, we'd need a pair of JSON objects. If we had a length 3, we'd need 3, and so forth. Each of these is an operator on many more types of JSON blobs. In the text of a JSON blob, we would simply add more cases separated by commas. Here, in order to create the tree structure, I've elected to make a binary tree whenever I want to add a new case. We'd have a head and a tail. If I organize things by branching by pairs of 2, they'll only need log base 2 steps to get to the bottom of the tree if I balance my tree. There are other methods, including hash codes, and much more deep thought goes into this. You should probably install a JSON parser for real life, but we're exploring the way to make one of these into a tree structure, and this will do. Now, what this has to do with evaluating things is that if I come up with a function that works on the letter J, then I can evaluate it on anything in this construction. I would simply have to tell you what to do with all of these different operations. And I'd have to do it in such a way that I could consistently apply it recursively. Once I reach a pair of values, I need to apply the same rule. This is where the world of algebra has a ready-made tool. Notice that we have homogeneous data. The type of morphisms that can transform homogeneous data are known as homomorphisms. Sometimes you'll have heterogeneous data when you have different values on this side, and then you would need a heteromorphism. To see a homomorphism, let's think of an application. We're going to be given something that's built from some of these constructors, but we're going to try to count how many different subparts it has, a very simple task. Let's see what we'd have to do to evaluate that map. The key to using an inductive type is to match the various patterns that are given to you, otherwise known as the operators. Those are the const n's, const s's, and so forth that we saw before. What I've done looks very similar to how I introduced the data. I'm simply writing the various cases that I had to introduce the examples, but now I'm giving them actual values. There's some s that was given, there's some n, so forth. When I come in with my JSON blob, I know it matches one of these patterns because I created it from one of these patterns. And if you add new patterns, you would simply have to add new cases. If you have dynamic data, such as these added base and next cases we had in our original example, they would be handled by a default case at the end, which interprets what those types have to be. What we want to do is count. So, since we're counting, we simply say we need to know the length of the string. When it comes to tracking the size of numbers, I put 4 because a typical number in a JavaScript type program will be 4 bytes long, and likewise a Boolean is less than 1 byte. I've just given it 1. And then when we get to an interesting case like the blob, we realize the blob depends on some other JSON object. This is our opportunity to use recursion. That is, calling the function count again on the data O. Whatever size O has takes the place of our size J because we're simply wrapping it with extra parentheses. The size hasn't gotten any larger. Null we count as 0. Here we have 2 objects coming in, a left and a right, that have been packaged together as one giant blob. We'll count that by simply adding the parts together. When we stand back, we see the structure looks like we've covered every case. And if we were, in fact, including other cases as defaults, we would have to add some processing to process those defaults. Keeping the situation as simple as we can, however, this captures the full length, at least to the degree that we want to model the problem. 4 bytes for numbers, 1 byte for Boolean, and so forth. Now, this by itself might be a program you would think of all on your own. You don't need very much algebra to come up with it. But let's imagine what we want to talk about is how do we consider patterns in general. Suppose that I want to change the program from a count to printing. What would I have to change to make that happen? Well, let's assume that when I print a string, I already have a command to print strings, and I have a command to print integers, and so forth. What I can see is the program changes very little. I still have all the same ways that I could have built the blob, and so if I handle each one of those cases, I will know how to print an arbitrary JSON blob. So my first operator is called asString. That meant I built it from one string. Well, then I should just print that string. Again, I'm assuming that our programming language has some primitive operations, such as printing strings, printing integers, so forth. When I get to the number, I print the number. Booleans can also be printed. When I get to the blob, this is when I need recursive application. In particular, what I'd like to do is demonstrate that I knew it was a blob inside of another one. So I'm going to print a header that says inside blob. Notice the potential for a little bit of confusion. This print is printing the string that will print to the screen contains, and that's followed by print O. That print O comes back to this particular print because the O is a JSON object, so it's learning how to print from us. It already knows how to print a string, so it got that from its own library. Nulls don't contribute anything, which we might indicate by simply putting in something like a new line character. Go to the next line. Once we're done with that, we're left with the concatenated blobs, one after the other. Perhaps these should each be printed on a line themselves, so we simply call a print function recursively with a new line in between. Once more, there's several versions of print here. This is the print that's inside of our library that already handles strings. This print is a JSON object. That was coming from the left side. It will therefore call our function and match it to the correct pattern recursively each time. And the right one will do the same thing there. At the end of the day, this is a modified version of our counting algorithm. For example, at the very end, instead of adding the length of left with the length of right, simply printing the left, putting a new line in, and then printing the right. To make a program that saves the JSON blob, I now give it in a file, and I'll return the same file that I'm writing to. Once more, I assume that the program already has some routines, such as writing strings and numbers and booleans, so I simply call fWriteS. When it comes to the blob, however, I need to make a recursive call. At this point, there isn't a write for JSON blob. After all, that's what I'm defining. But what I can say is that I simply want to pass that O along to my save file. Null is a case where I don't have anything to add, so I simply return the file as is. Finally, when I've concatenated two blobs together, I'll need to save the two parts. The result will be that I've saved all the data into this file. Now, while each of these functions achieves a different task, they do so in roughly the same way. We simply go through the case analysis of the ways we could have built it, and then we apply certain logic to the end of it. What if we just simply gathered all that logic into one package and passed that along? Then we wouldn't have to program a new function every time. That is, this starts to look like boilerplate. If every single function that works with JSON has to go through these operations, then maybe we should save ourselves time and just articulate the logic of that. Let's go back to our counting problem. When we wanted to count, remember we had various operators. I've only focused on two of them, asString and the concatenation command, but you can do all the others as well. In the asString situation, we start with an empty list. That's one object. One object can only be mapped to one object. And in fact, there's only one object to map to in NT0. But when it comes over to here, if we were to try to think of a function that goes from j to n, it would have to be assigning what we think of as the count. Remember, the count was the total number of data that we needed to store. So what we see here is that we wanted to turn this string into the length of that string. The operation that's matching the asString for the JSON blob is the operation length for strings. When it comes to concatenation, what did we do? Well, we took the lengths of the left and the right-hand sides, and we added them together. So the effect of counting that JSON blob should break up into making two separate counts, the count on the left and the count on the right. We write count squared to think of the function that's writing count on the first part of j and the second part of j. Keep in mind, things in j squared are ordered pairs. Remember that our cat is taking our left and right blobs and gluing them together into one common blob. If I want to count them, we said we should count the two independent sizes and add them together. So if I'm trying to define this, that was my goal. But why was that naturally chosen? Well, I can see that left has to go to the count of left. And right also is being counted. When we apply addition of those two numbers, we indeed end up with counting the left and counting the right. We can put this all together into a simple formula. If we trace this all back, we see that cat is the binary operation from j squared to j. Meanwhile, plus is the binary operation from n squared to n. We're simply matching up two different algebras, and this is all the way back to our base cases, the ones that depend on just constants. Because all the operations are homogeneous, meaning they depend only on one type of data, in this case j or n, the pattern that we're doing is preserving the homogeneity and all its operations. Hence, these are called homomorphisms. And this applies to all the operations that are in our algebra. Take, for example, the object block. So that gives us a clue for what the natural number operator should do to this count. It should simply return the same count. In all the homomorphisms, the idea is to match the inside operations of the abstract object, the JSON blob or the other inductive types, with the outside operations, the new data we're trying to study. That might be saving a file one day, printing the next, counting the third day, or any number of new operations that you will come up with in your daily life. So the key thing we've hit upon is that everything here can be written down as operators in algebra and matching them up by these diagrams that must commute. So for example, if I wanted to save files, I would simply think of this part as saving all the primitives. At the end of that, everything else is taken up by recursion, and no more thought is necessary. What we're saying is that inductive types are a type of algebra which can transfer all of their operations to anybody's future algebra. This is what's known as an initial algebra, and it can be a very powerful way to glue together information. We gather together a set of all the cases. We call that omega the operators. Each operator has a valence. That's how many times the values will depend on previously built values in J. So if the things don't depend on any other values, they'll be 0 for the valence. But if they depend on one previous value, it'll be 1, two previous values will be 2, and so on. In our JSON example, we could see that as string had a valence of 0. It didn't depend on any previous JSON blobs, but object depended on 1. It had a valence of 1. And the concatenation operator had a valence of 2. So now we're ready to describe the unique feature that makes inductive data types what they are. They're the things that have the elimination rule given by a homomorphism. That is, something that preserves all of the operators of this algebra. We can write that with our cartoon diagrams. What we need is a set of operators. Those can be plus signs, those could be as string, cat, minus signs, whatever operations come to your mind. Once you have those operations, to make an inductive data type, you need to have an operator for every single operator in the big set of operators. So if I have any other type of data with an omega algebra structure, what do I mean? I mean that for every little operator in the big operator set, there's a function with a matching valence, just like we said in the beginning one here. So both J and A are algebras of the same set of operators. For example, they would both have an as string and a cat if we were in the JSON algebra world. So what's special about the algebra J as compared to the algebra A? We can see it in this last diagram. What this diagram says is that there's a unique function that goes from J to A. That unique function satisfies the following picture for every single operator, little omega inside of big omega. For example, if this was to take a 0 number of inputs to J, such as string, then the corresponding number down here would have an as string operator that takes in 0 values and spits back 1 value in A. But it would do it in such a way that it matches whatever the result is on the total data set. So if we later have a concat, the concatenation would take in 2 values, the operator here would take in 2 values and return a value A. It's completely defined by what it does on those operators. This means that we can stop worrying about the data structure J altogether. All we need to do is figure out what we want to do with future algebras. Those future algebras will have many concepts. We might have an algebra for printing, an algebra for saving, an algebra for transmitting on the web, and an algebra that measures how big the files are. Their combined behavior is based on the fact that the algebra is constrained by this homomorphism. We cannot do one operation here that would be matched on that one there. The uniqueness of this map should hint of the universal programs we've seen before. What we're doing is we're matching a specification of a data type to any future program. This will allow us to migrate or move the data around in ways that are predictable. We don't have to think as hard because once we know we've built an inductive data type, we know exactly how it can be used by anyone who wants to use it. That makes for predictable programming, easy refactoring, and basic understanding of what's going on. In fact, this is so strong that we can replace A with a value of proof, what are known as propositions. When we replace these with propositions, statements of truth, we can think of this as writing a proof. The result is known as a proof by induction, which is a whole different topic, which we'll cover in another video. Until next time. That's how you take care of your chalkboard.